This lesson is for Chapter 5, Section 2, Logarithmic Functions and Their Graph. Please get your notes out and ready. You probably should have your graphing calculator handy, or a calculator with a log button on it anyway. And your book's open to page 373. All right, so this expression that you see on this first slide for definition of a logarithmic function with base a is kind of a key piece to understanding today. So make sure you write it down, take a look at it real close. It says y is equal to log base a of x if x is equal to a to the y power. Okay, so it's just a rearrangement and a remanipulation of the same numbers and the same pieces of both of these versions here. So we've got to get comfortable with working this both backwards and forwards between these two forms. Let's take a look at evaluating some logarithmic functions at a given value. This is the checkpoint problems that are on page 373. The textbook has some more, so look through all of these and see if you can't make some sense of them. Let's do these three together. Letter A says f of x is equal to log base 6 of x when x is equal to 1. So if we're going to evaluate that, y is equal to log base 6 of 1 would be rewritten as 1 is equal to 6 to some power of y. Well, the only power that we could put on a 6 that would end up giving us a value of 1 is the 0 power. So in this particular one, the value of y has to be 0. Letter B, f of x equals log base 5 of x if x is equal to 1 over 125. So y is equal to log base 5 of 1 over 125 can be rewritten as 1 over 125 is equal to 5 to some power of y. Well, 1 over 125 is the same as 5 to the negative 3 power. So in order for 5 to the negative 3 to be the same as 5 to the y, negative 3 has to equal y. Third one, f of x equals the log base 10 of x if x is equal to 10,000. So log base 10 of 10,000 is equal to y, which can be rewritten as 10,000 equals 10 to the y power. Well, 10,000 is 10 to the 4th. So for this problem, 4 must equal y. On your calculator, find your log key. Okay, example number 2 in your textbook on page 374 shows how to use the log key. Go through it and try those examples and make sure that you end up coming up with matching values to your textbook. There are some more problems there that use with the checkpoint problems where you can practice them on your own. And I didn't do those on the slide here just for the sake of time. But if you wanted to check your answers there, just log on to that larsonprecalculus.com. Properties of logs. Okay, so these are some relationships, again, that we're going to need to try to become familiar with. Look through them. Take a look at the relationships between them. Log base a of 1 is equal to 0 because a to the 0 power is equal to 1. Log base a of a is equal to 1 because a to the first power is equal to a. Log base a of a to the x is equal to x. And a to the log a of x is equal to x. Those, we will play around with them a little bit more in the future. We're going to show you that those two are inverses of each other. Remember from the past, if functions are inverses of each other, you should be able to swap x and y with each other and simplify and reduce. So that's kind of what's going on there in those two pieces of step number 3. Okay. Number 4, if log base a of x is equal to log base a of y, then x is equal to y. That's called our one-to-one property. So if the log and the base are a match, the two things that are used in them, the x and the y, also would have to match. So checkpoint 3 puts some of these to work. Say simplify the following. So on that first one there, simplify log base 9 of 9. This is going to equal 1 because 9 to the first power is equal to 9. Okay, so it's utilizing those properties on the back side there. Remember, this is log base A of x. So 9 is the x, A is our base, and then 1, of course, is the y. Okay? B, let's try that one. Simplify 20 to the log 20 of 3. This one goes along with this property, number 3. So putting that to use, if you have 20 to the log base 20 of 3, you're just going to get 3. Okay, again, study that expression and go back to that property number 3, and I think you'll see that relationship. Letter C, simplify log of root 3, 1. This one, again, is just going to follow that property with the a and the x. Log of base root 3 of 1 can be rewritten as root 3 to the y is equal to 1. And then if you're going to have, again, anything raised to a power and equaling 1, it has to be raised to the 0 power. So this is another one where y would end up having to equal 0. Checkpoint problem number 4. This is using that one-to-one property. Again, that was listed with those other properties on that table. Solve log base 5 of x squared plus 3 equal to log base 5 of 12 for x. All right, notice that our log base 5 is a match in both pieces of our problem here. Whoops, I made my line too short. So this much matches in both, which means these parts have to be matches. So go ahead and take them and set them equal to each other and figure out what it must end up being. Now we have an x squared in this one. Let's solve for x squared. If we end up with x squared is equal to 9, x will end up being either positive or negative 3. Some graphs to sketch. Okay, it says sketch the graphs of the following on the same grid. Now it says that f of x is equal to 8 to the x, and then g of x is equal to log base 8 of x. When we look at this, remember, this means y is equal to 8 to the x. Okay? So if you wanted to come up with a set of points or a table of points, just pick a few random x's. I chose negative 2, negative 1, 0, 1, and 2. And if we plug those in there, 8 to the negative 2 power is 1 over 64. 8 to the negative 1 power is 1 over 8. 8 to the 0 power is 1. 8 to the first power is 8. And 8 to the second power is 64. Now obviously some of those points aren't going to land on our graph, but you'll get an idea of how this curve is going to go. At negative 2, we barely move off the axis. At negative 1, we still don't go very far, but a little bit higher. And then 0, 1 is our intercept on the y-axis. And then 1, 8. And of course the other one's going to shoot right off. So here's our curve for 8 to the x power. Now g of x is set equal to log base 8 of x. And if we rewrote that one, we'd end up with 8, well, x is equal to the base to the y power. Okay, so that came from our previous slides there. So x is going to equal 8 to some power of y. Now with this one, when I came up with these values, I actually chose my y's because it was easier to pick something and put it in for y than it was to put something in for x and figure out what power of 8 equaled that. So I went with these values over in my y column. So if I put negative 2 in for 8, I have 8 to the negative 2 power, or 1 over 64. For negative 1, I'm going to get 1 over 8. For 0, 1. For 1, 8. And 8 to the second power is 64. Now compare your two tables and notice something about those pairs of points. They're just flipped. Okay, so there's our proof that these two functions, take a good look at them, a to the x power and log base 8 of x, they are inverses. So if I came over here and graphed my g of x, I'm going to have at barely anything, I go down here to -2 and -1. 1, 0 is my intercept. 8, 1 is another point. And this curve comes over here and shoots. So when you look at them, you can see that they are a reflection of each other. Okay, they are inverse functions of each other. The other thing that our textbook points out to us is their line of reflection is the line y equals x. Okay, that diagonal line that goes through here is their line of reflection. All right, sketching this one next. Again, this can be rewritten from what we have right here. We can rewrite that as x is equal to a to the y. So x is going to equal 9 to some power of y. Okay? This was another one of those cases where I decided it might just be easier to pick my y values than my x. So I went ahead and I grabbed a couple random numbers here. Same numbers as before, actually. So if I put 0 in for the power of 9, I'm going to get a value of 1. If I put 9 to the first power, I get 9. 9 to the second power, 81. 9 to the -1 power is 1 over 9. And 9 to the -2 power is 1 over 81. So coming over here and sketching then, 1, 0, 9, 1. The other one obviously is not going to fit on our graph. 1/9 -1, and then 1 over 81, -2. And again, we can find what our curve is going to do. Okay. All right. Vertical asymptote, notice. What value is x never going to reach? If we kept putting in different values of y here, we're going to get smaller and smaller and smaller numbers, but we are never going to get an x value of 0. So this particular function, when you look at it after it's being graphed, does have a vertical asymptote of x equals 0. Okay, now this leads us into a couple of things that we have listed here as summaries of these logarithm graphs. You will find you have a domain of 0 to infinity. We just talked about that. The x value will never end up being 0, but it could go off to the right up to infinity. Our range, if we come back here, our y values, they can dip down low into infinity, and there's nothing to bound them from getting higher and higher either. So our range, or our y values, can go anywhere from -infinity to +infinity. The x-intercept we found is 1, 0. The function is increasing. It is 1 to 1. Now remember, the test for 1 to 1 functions was that horizontal line test. Okay, these functions that we've been graphing would pass that. Any horizontal line passing through that curve is only going to intersect it in one place. Passes that horizontal line test, we know we'd be able to come up with an inverse function. The y-axis is your vertical asymptote. We talked about that already. That's your x equals 0 line. It's continuous. There are going to be no breaks in that graph. And the reflection is going to go over the y equals x line. Now, when we look at these functions, the transformations we used on other graphs in the past are going to apply again. We saw those transformation things creep up in chapter number 4, so it hasn't been very long since we talked about them, but you just may have to go back to section 2.5 and review those shifts to parent functions found in that section. So checkpoint number 7, it says use the graph of f of x equals log base 3 of x to sketch the graph of each function. All right, so if we're going to go along with the log base 3 of x and a minus 1, okay? Um, Looking at values and putting this in here, log base 3 of x would be rewritten as x is equal to 3 to some power of y. Okay, we've been working with that already. That should look familiar. And then we still have that minus 1 in there. Okay, remember from the past, what does it do to our graphs if we have a minus 1 tacked on the end of our function? Okay, that one was that vertical shift down 1. Okay, so looking at this then, we can still build our table of values. And if we're looking at 3 to the y power minus 1, again, you just might want to start with y's instead of x's. So if we have 3 to the negative 2 power, that's going to be 1/9. If we have 1/9 minus 1, we have negative 8/9. If we have a minus 1 power, we're going to have 1 over 3 minus 1, or negative 2/3. If we put a 0 in there, 3 to the 0 power is 1. 1 minus 1 is 0. If we put a 1 in there, we have 3 to the first power, which is 3. Subtract 1, we're going to get a 2. If we put a 2 in there, 3 to the second power is 9 minus 1 is 8. Okay, so this gives us an idea of what this curve is going to look like. At negative 8/9, we're going to have negative 2. At negative 2/3, negative 1, 0, 0, 2, 1, and 8, 2. Remember what the x or the y-intercept was of our parent function? Remember how the n-intercept's always going to be 0, 1? See our down 1 shift to having our intercept here at 0, 0 now. Okay, so those shifts still apply to these functions just like they did those other parent functions that we talked about. Let's take a look at another one. If you add 3 to the actual x part, remember adding or subtracting on here, this was our left-right shift. So if it's a plus 3, this function is going to shift left 3 places. All right, so looking at this again, right now we technically have y is equal to log base 3 of x plus 3. If we rewrite that, we'd have x plus 3 is equal to 3 to some power of y. All right, table of values. Okay, I just went with a few this time. We'll get the idea. If I put 0 in for my power of y, I'm going to get x plus 3 equals 3 to the 0 or 1. Solving, x ends up being negative 2. If I choose 1, then I have x plus 3 equals 3 to the first. Subtracting 3, I get x is equal to 0. If I put in 2, then I have x plus 3 equals 3 squared, x plus 3 equals 9, or x equals 6. And the last y that I chose, if I put that in there, I have x plus 3 equals 3 to the third, or x plus 3 equals 27, or x equals 24. So negative 2, 0 is 1 point. 0, 1, oops, wrong, negative 2, 0, let's try that again. Now we can do 0, 1, 6, 2, and of course the other one is not going to be on our graph. And we're going to get this. Now remember what your vertical asymptote is on your parent function. It's the y-axis, the x equals 0 line. Look what our asymptote appears to end up being now. The x equals the negative 3 line. And there's evidence of that left 3 shift. Now, the natural logarithmic function, it's also called the inverse function of f of x equals e to the x. It's defined by f of x equals log base e to the x, or simply ln of x. Now look at your calculator real quick. You'll find that not only do you have that log button that we've already been playing with, there's another button on there that just says ln. That's your natural log key. All right, so then it follows then that y equals ln of x and x equals e to the x mean the same thing. It also means that f of x equals e to the x and g of x equals ln of x should be inverses of each other, and their graphs will end up being reflections. I know it's confusing when they throw in all of these logs, these e's, these x's. They get much easier, I think, when we play around with them with actual numbers in. Now, evaluating natural logs with a calculator. Practice with example number 8 on page 377. So they give you 4 of them. They give you keystrokes and steps to follow and displays that you should be seeing. So give each of those 4 on page 377 a try. If you want to play around with it where it doesn't give you the keystroke, the checkpoint ones are right underneath there, another A, B, C, and D. And you can evaluate that yourself with the precalculus.com site again. Now notice the error message. You can see that on their letter C in example number 8. When you see that, okay, when we put in -1, that was the one that resulted in that error message. Okay, look back to the summary of law functions and see that the domain is 0 to infinity. Well, if we punched in ln of -1, we chose an x value that was out of our domain. So only positive values are going to be able to be evaluated in these problems. Okay, even if you stuck a 0 in for x, you're going to get that error message. So I thought it was kind of cool that the book actually had us do that and see that error message pop up on our calculator. And that's why. That value of x is not in our domain. It's going to give you something that's undefined. Properties of natural logarithms are as follows. I'm not going to read them to you. You can read them to yourself. Notice that 3, again, is one of those statements that shows or indicates inverse functions. Also, number 4 is that one-to-one property. If the natural log of x is equal to the natural log of y, that means x has to equal y. All right, so let's play around with a couple of these. Letter A, if we have the natural log of e to the 1/3, based on our properties, we're going to get a value of 1/3. Letter B, we have 5, natural log of 1. This is going to equal 1, 1, because the natural log of 1 is 0, and 5 times 0 is going to end up being 0. Oops, no, I was right. Come back. It does give us a value of 0. My finger dropped to a wrong line. All right, the next one, 3/4 natural log of e. That's going to end up giving us 3/4 times 1, which of course is 3/4. Then we have e to the natural log of 7 power. And again, using your properties, you're just going to get a value of x, which in this case was 7. Finding the domains of the log function. Okay? Now, finding the domain here, if I have an x added to my function value, or an amount added to my x in my function value, again, that's going to be that left-right shift. So the +3 is a left 3 shift. Okay? So if we have x being x plus 3, remember how our x values had to be positive? So that means x plus 3 has to be positive. All right? So if we're going to evaluate the natural log of something, we still have to keep it positive. So in this case, we have to keep that x plus 3 greater than 0. So solve. x has to be greater than -3. And then that's going to identify that domain. We can't have anything under -3, but once we start there, we can go all the way up to infinity. Checkpoint problem number 11. I did an application problem with you guys this time. We are going to be looking at some of these functions. The last section had us working with compound interest functions. This one has, with example number 11, in your book, if you turn to page 379, it's just talking about a model that was developed. It was a human memory model. So don't worry so much about where they got that. We don't need to know that. We're not the ones to develop that. We're just going to use it. So if our function is this, we want to evaluate that same score. It's talking about a memory score of how many problems you would still get right, or percentages or something like that. Find the average score at the end of a month. Well, in that model, t represents time in months. So all you have to do is plug in 1 for t. And if we evaluate that, then 75 minus 6 natural log of 2. The natural log, or ln of 2, times 6, taken from 75. Now when I entered this into my calculator, I just went from left to right. So I had 75 minus 6 ln of 2, and I hit enter. All right, so the keying in of this isn't any more difficult than that. Punch it all in at one time, and it gives us this value. 9 months then is the same drill. 75 minus 6, natural log of 9 plus 1. Whoops. ln of 10. Punch that all in. And the final one, 12 months. And we end up with 59.61. Now the results from this are not all that surprising. If in fact this was some kind of a human memory model, as time goes on, you're going to forget some of the information that you once upon a time knew. So after 1 month, they still remembered 70 or 70%. It didn't really say what the score was out of, but I'm just going to pretend it was percents. After 9 months, it was down to 61%. After 12 months, it was down to about 59.61%. Okay. Sorry, that's what I got for you. The assignments come, or the problems come off of page 380 to 382. Work on some of those word problems like that human memory model. Play around with some of those model problems. They're really not that bad.